going to do today is chapter 8.3. I'm going to get that finished. That's my goal. There'll be my other statistics class. You'll be able to watch the video of that. They will also have 8.3 getting finished, and they will get started on 8.4. We're a little bit out of sync, but that's just the way things are. Next week, we only have Tuesday, because in your case, only Tuesday, because Thanksgiving. So next week, I'll only see you for one day, and then the next week, I'll see you for the typical 2. So anything that we don't get caught up on, you're going to have to watch on the videos to make up for that. Just the way the holidays are working, you're losing a disproportionate number of days, I think. Okay, so what we're going to do, we're going to look at hypothesis testing. In fact, 8.3 is hypothesis testing with 1 proportion. 8.4 is hypothesis testing with 2 proportions and with 2 means. So you're comparing 2 different things in 8.4. Here we're just comparing one thing against a fixed value. So here is my made up example, and we're going to do it in 2 ways. I am going to show you the slow, long way, but I want you to at least see once in your life what it looks like by calculator. And then we'll show you that you can do pretty much most of it, but not all of it on salt. So here is an example that I'm going to do using the calculator. It's a pretty standard looking 8.3 type question. So in a small town, the percentage of people who own their own homes is 68%. So that's like a historical average. And then we go on a bit further. A survey was conducted to see if this has changed. So what the guy did is he randomly selected 120 residents, and he found out that 78 of them owned their own home, right? And we want to then use that information to test the following hypothesis. Is there enough evidence to show that the percentage of people who own their own home has reduced? And by reduced, has reduced from 68%. And we're going to do it using a 5% significance level. So first thing you're going to do is you're going to state the null and alternate hypothesis. We've had quite a lot of practice at this, so it's very similar. There is one kind of major difference. When you do means, isn't it always mu greater than 7, mu equals to 7? They always use that Greek letter mu. But when you do proportions, it's not mu, that's the mean. When you do proportions, it's P that you use. P is the population proportion. So that's the population percentage who own their homes in this story. And we read this bit here again, and it tells us who the alternate is. Show that the percentage, show that P has reduced. So show that P has reduced. And you notice that you use decimal version, not 68%, but the decimal version of it. If this guy is less than 0.68, this guy is always equal to the same number. Isn't that just like the, mu greater than 40, mu equals 40, right? So that same basic pattern. The alternate always has a less than, a greater than, or a not equal to, right? That's the 3 stories. The null is equal each time, right? I'll ask a question. Does anybody know if that's a left, right, or two-tailed test?
That'd be left, I believe.
It is. Basically, it's pointing that way, right? It's pointing to the left. So that's step 1 done. Do you know that if you're using salt, what salt would do is it give you four combinations, and one of them would be this one, and then the other 3 would be wrong. So you just pick the right one. So that's how they ask the same question online, right? This would be one of the choices, and then there'd be 3 that were different in some way, and you could only choose that one. Now you collect the z-score and then the p-value. The formula for getting the z-score, well, it's p hat take away p over the square root of p 1 minus p all over n. Or, in other textbooks, you remember that q is just 1 minus p. So just in case you see that, it's the same as this. Now, I know who p is. It's 0.68. In this sample, I know that n is 120. That's good. P hat is the number of people who own their house. In this case, it's a percentage, right? So it's 78 over 120. And 78 divided by 120 comes out as 0.65. So using all these guys, here they are, I should be able to get a z-score. Nothing 0.65 take away nothing 0.68 divided by the square root of p 0.68, 1 minus p 0.32, all divided by 120. So see if I can do that in the calculator. And it looks something like this. Put a little bracket around it, 0.65, take away 0.68, close the bracket, divided by a big ugly square root, 0.68 times 0.32 divided by 120, and the answer I've got is negative 0.7. Well, if you want to be more accurate, 705 to 3 decimal places. Are we okay with that? How you get a z-score? You just need to know what formula to use. We've done that. Now, how do you get the p-value? It's the probability that you get a z-score less than that negative number. If this is less than, that will be less than. If z-score is negative, that will be less than. So there's two ways you know that it's less than. We do that by getting a guy called normal CDF, which is the same guy we used, you know, in other sections. I'll show you what that guy looks like. In this case, negative 9, that fella 0, 1. That's always 0 and 1. When it's less than, it's negative 9 and the number. When it's more than, it's number, comma 9. So there are only two versions. This is the less than version. So second distribution, number 2, and you type in negative 9, comma, negative 0.705, comma, 0, comma 1, and the answer we get for the p-value is 0.24. And that's step 2 done. Step 3 is we test. And we test, is our p-value less than the significance level alpha? In this case, is 0.24 less than, what's my story? 5%. And the answer here is no. When the answer is no, you will do this. You will pick this choice. You fail to reject H naught, and the result is not significant. And you will also have a question that says, what does that mean in English? And it means in English, there is not enough evidence. It's just one of the ways to say it, to prove this statement. So rather than me rewrite that entire sentence, you can just say, look, there's not enough evidence to prove it. Suppose that p-value was 0.02, right? Something nice and small. Then wouldn't the answer here be yes? And if it's yes, you would reject, oops, two fails here. You reject H naught, and the result is statistically significant. And there is enough evidence to prove the statement. And that's how you would do it, basically, mostly with a calculator. So you have step 1, hypothesis test. Step 2, calculate the P and Z scores. And step 3, test. Now, with that same story in mind, I'm now going to go to our calculator at our WebAssign, and we're going to show you how you would do it in WebAssign. Okay. So I'm going to, first I have to switch over so you can see it. Now, the good news, as far as I'm concerned, is that once we've done 2 or 3 of these, you'll start seeing that it's really pretty much the same question every time. They just change the numbers, right? It's the same kind of question. So I hope you're looking at, let's make this a little bit bigger. Are you looking at question 3, for instance? And so, is that what you're saying on your screen? A thumbs up would be handy. I don't know what you're saying if you don't tell me. Oh, perfect. Okay. So I'm just using the salt button for my question. When you hit salt button, this appears. Now, along the top, there's lots of choices, and it depends on what you're doing, which choice you want. But for these questions, this is the one that you're always going to use. It's called inferential statistics, right? Infer, I'm going to think about something, try to prove something, that word, infer. So when I click on it, procedure selection. When you click in this, there's a number of choices, but the one we want is called one sample proportion. So you pick that one. Now they have a funny way of saying it, but number of successes and number of trials. In this story, we went and asked 128 people, and 78 said they had a home that they owned and lived in, out of 120. Do you see where those two numbers are then? 78 out of 120 in my sample owned their home. You then move down to the hypothesis test part. And in our case, it was 68, right? And we wanted to see whether it was now less than. And if you switch them round, it makes more sense. We want to prove, right, the hypothesis test, that it's less than 0.68. So once you got all that done, you hit generate results. Do you see the Z statistic and the p-value that I calculated by hand? Right, negative 0.704, what did I say it was? I said negative 705, we'll not argue over that because I rounded it up, right? and I got a p-value of 0.24 and exactly the same guy. Do you see it now works? So far, so good. If there are any questions, feel free to ask. So we are now going to do as many questions as I can get covered in the time that, oh, great, thanks, Bailey. In the time that we've got here. So this is question 3. Not much of a story behind it, but it's still the basic question. You did 40 trials. They're called binomial. Binomial just means there's only a yes or a no, right? So you did 40 trials, 16 successes. Tested claim that the proportion of successes does not equal 50. Okay, so I'm writing that number down because it'll disappear in a second. I get 16 out of 40, and I want to test that it's not equal to 0.5, and the significance level is going to be 0.05. Okay, should be good for that. Click on salt. You got this. One sample. In this case, it was 16 out of 40. We're checking, oh, perfect, that it's not equal to 0.5, and we're good to go. And the numbers that we have here, or the stuff that we have here, is pretty much step 1's done for us. Can you see the null and alternate hypothesis? There's my Z statistic, but much more important than that, here's my p-value. And in this case, the p-value is 0.205903, and the Z statistic is negative 1.269. So let's see what that looks like in the homework. Well, they start off with a question we haven't talked about yet. Can you even do this process? And the answer is yes, you can, provided n times p and n times q are both bigger than 5. So the test here, excuse me, is the number of people who said yes and the number of people who said no, are they both bigger than 5? Well, 16 successes, 16 said yes. That makes it 24 said no. We are good. So you will click on that dot. Now, the null and alternate hypothesis, we had it a few seconds ago, but now you can't see it. It was that one. Compute p hat. Oh, I missed it, but p hat is 0.4. I'm not going to go back, but it's in that table, right? If you go and look at it. Compute the standardized sample test. That is them asking you for the Z score. So there you type in negative 1.2. What did they want it to? 2 decimal places. So 1.27. Find the p-value to 4 decimal places, 0.0205. Now, these two guys are the test. Is our p-value, oops, I put a 0 in there that I shouldn't have, is 0.205 our p-value, is it less than that number? And the answer is no, it's not. So at that level, we fail to reject the null hypothesis, and it's not statistically significant. So when you do know, this is the sentence that you use every single time it's a no. You fail to reject the null, and you conclude that the data is not statistically significant. And how do you put that into English? Well, here's what it's not very good English, but it is better. the sample value based on is not sufficiently different from 0.5 to justify the answer. And we are done. I'll not do that one. It's a pretty boring question. It's the Beneford's Law one again. Right, let's do 6. In the national crime rate really going down, some sociologists say yes, it is declining. So let's check it out. The historical number is 70%. We're going to check here that in this place called Rock Spring, Wyoming, 33 were arrested last month and 21 were in that age group. So according to this data, do you know that 70% of the arrests are for technically young people between 15 and 34? And the vast majority of them are males. So if you're going to get mugged or your house broken into or your car stolen, 70% of those are likely caused by people in that age group. Anybody got any ideas why that age group, and males in particular, seem to commit more crimes than any other age group, or females?
Less brain cells?
That would be an insult. It might be true. It's interesting when you look at that. But I've no evidence. Here's my version of that. Do you know once you get to, let's say, your mid-30s onwards, we would hope by then that you've matured enough and that you realise that unless you're a hardened criminal, right, and that's your life, you've probably figured out that it's not worth it to commit the crime because going to jail isn't that much fun. Secondly, I hope that most of them have settled down into a stable relationship and maybe have children. And you know, when the minute you start getting responsibilities, aren't you less likely to do things that are going to land you in jail? So that's just my argument for it. It may be nothing like that, but that's what we're doing. So we've got all the information that we want there, and I will return to it, but here's the silliest question in the world. Use a 5% significance level. What is the significance level? Would you agree that question is so silly it's almost worth not asking? Right. Now, we are trying to test here this claim that the population proportion is different than 70%. One of these 5 dots, number 1, 2, 3, 4, or 5, one of these corresponds to is different than 70%. 1, 2, 3, 4, or 5. I got it. Yep, let's check it out. Do you see not equal to is just another way of saying different? And isn't that one the same number as that with an equals? Can you do the sampling? Yes, you will. You are going to be doing that sentence every single question. So by the time you've got to the third one, you'll know what the answer is, right? NP and NQ are greater than 5. Now, these two fellas are going to come from the data. So I'm going to have to go back here and I'm going to make sure that 33 out of 33, 21 were in that age group. And then the other thing is 70%. Okay, I got it all. Use salt. Let's try and move it again. Here we go. Oh, I can't use that salt. That's already in the table. Right, I can use this one. So we have 33. Out of those 33, 21 were in the age group, the younger age group. We want to see, is it different, right, not equal to 70%? And I got those two numbers the wrong way around. I'm glad the software is paying more attention than I am. There. Green, good to go. Generated results. There's your null alternate. The z-score is negative 0.79 and some sevens, and the p-value is 0.4205. Sample statistic is our z-score, so it is negative 0.797. P-value 0. Can't read my own writing. 42, there we go. 425. Oh, 4250 to 4 decimal places. Now, one of these 4 pictures, right? One of these 4 represents what's going on. Isn't this a two-tailed test because it's a not equals to? And do you see that the only picture that has 2 sides to it is this one? 0.42 is too big. That means you ain't going to reject the null hypothesis, which makes it that one. We fail to reject the null hypothesis and it's not statistic. And that one, for how you interpret it in English, insufficient evidence to show that it's different. Are we good? Haven't found a success yet, so I'm going to skip by the women's athlete one because I know that one's a non-success story as well. It's not significant. Okay, so this one is question 8. What do we have here? It says that the national rate is that 77% of all fatally injured automobile drivers were intoxicated. So that pretty strong evidence why you should never drink or drive. Or be in a vehicle where the driver is drinking, because he's just as likely to kill you as himself. So 77% is pretty big. In a certain county, they checked it, and out of 52 fatalities, 35 were intoxicated drivers. And we want to see, does this data indicate that the proportion is less than 77? Okay, so significance level is 10%. We're looking for a less than story, which makes it that one. You know this guy, you've seen him enough times. Right, test statistics, p-value, conclusion, coming up. Hit salt. Excuse me. One sample. In this case, I know it's a bit cruel, but success is how many people out of the total number of 52 were intoxicated, which is this guy. And we're comparing it, is that number different than, what's the question? Is it different than 77? And it's not different than 77, it was actually, is it less than 77? So 35 out of 52 were intoxicated. Is that evidence to prove that it's less than 77%? There we go. The p-hat is 0.673. The z-score is negative 1.660. And that p-value is nice and small, 0.04837 and some other stuff. Z-score, negative 0.797. P-value, 0.048. Oh, I need another digit, 484. Now this is a less than story. So the one that's got a less than is this fella. Now, is 0.048 less than 0.05? And the answer is yes, it is less than it. So when it is a success, when it's a yes, this is the sentence that you're going to do. That one. We reject the null hypothesis and conclude that the data is statistically significant. So that's the sentence that you pick every time it's a yes. And every time you get a no, you pick this sentence. You see the difference? You fail to reject and it's not statistically significant. This is a yes story, so we pick this one. You reject the null and it is significant. And here, you pick that one. So we have shown here that in that particular place, there's less drunk drivers than others. Do you know which places have more drunk drivers than others? I happen to know this. Are rural areas, right? Places that are less inhabited, got lots of farmland or just lots of nothing? Or is it cities where there's lots of people, all closely packed? Which one of those two has the highest incidence of drunk drivers? Anybody know? I thought it was interesting when I found this out. I was even, at least in the article I read, it even gave me a reason. It's the rural areas. I would have thought it would be the big cities. You know, lots of nightclubs, lots of bars, lots of places to get drink. There's going to be a lot of people drinking and driving. But they're actually, there are people who do exactly that, but they're actually less. It's the rural areas that have a higher incidence. And the explanation went something like this. If you live in a city, can't you, forget COVID, but couldn't you get a taxi home? Or the subway? Or I guess if you're really stuck, you know, buses. So you can go out and you can drink and not need to really, it's relatively easy to get home, isn't it? Right. Now, if you are in a rural area, you don't really have that. Don't you probably use your own transport to get everywhere? So if you drive into the nearest village to get, you know, to have some alcohol, isn't there a good chance that you're going to drive back in the same vehicle you came with? And therefore, you're probably going to be a higher number of people who drink and drive. So rural areas that aren't, you know, don't have a lot of things in them, tend to have a higher incidence of that. And secondly, which is, I made this up, that wasn't in the article. If you live in a city, isn't there a good chance that there's a few cops around? So you're more likely to get caught, and that's a deterrent. In a rural area, couldn't you go for miles and miles and miles and never see a cop car? So your chances of being caught are much less. I'm putting that in as my extra reason for that. Okay, this is interesting, I guess. I haven't done this one before, so I don't know how it's going to work out. It's question 9. What's your favourite colour? In a large survey of countries, including America, China, Russia, Turkey, I mean, lots of places, Kenya, indicated that most people prefer the colour blue. In fact, about 24% favour the colour blue. So if you went and said, what's your favourite colour? There's a 1 in 4 chance that you'll say it's blue. Okay, you're going to get a chance to put a thumbs up here. How many of you have a favourite colour of blue? Okay, 2 out of 6. Kind of supports that argument. Now, suppose a random sample of 60 college students. So I've just did a random sample of you lot, right? And 14 of them, R equals 14, said that blue was their colour. So basically 14 out of 60. Let's pretend that was Olympic College, right? 14 people out of the 60 I asked, blue was their colour. Let's do the thing. Does this imply that the colour preference of college students is different than the general population? Right, the significance level is that number. When they say different, they mean this fella here. Right, not equal to is different. What is the sampling distribution? Why can you do it? NP5, NQ5. And now we can get into the salt part. And one sample. Number of successes, 14 out of 60. And we are going to compare it against 24%. Okay. So is it different than 24? And there is let me check that data. Wow. I was just surprised. Do you notice how big that p-value is? It's 0.9. Well, it's not a surprise. I just did the calculation. Do you know 14 out of 60 is about 0.23? It's virtually the same number as 24, so no wonder it's so big. So if you go here, then you're simply just going to put in a Z, the Z score, which I have in front of me now, is negative 0.12. And that gave you a ridiculously high p-value of 0.9037. Right, if you look at this picture, can you see it's that one? Two-sided with almost nothing left. Failed to reject. Not statistically significant. There is insufficient evidence. Okay. Now I'm going to return back to that in a few minutes, but I want to do something here, if we can. Right. You're going to get a Z score. Whoops, I don't know if I put this on the right thing. Let me make sure I have. You're going to get a Z score. And then the Z score is going to lead to a p-value. These two things are very, very closely related. If you get a Z score that's big, the p-value will be correspondingly small. So if you get a Z score of something like 2.56, you might end up with a p-value of 0.008. If, on the other hand, you get a Z score that's small, the p-value gets big. So if you get small, like 0.81, then the p-value could be as big as 0.56. So when I look at these questions, I can get a kind of rough idea what's going to happen before I even calculate most of it. See, if you get a z-score that's bigger than 3, your p-value will be so tiny, I can guarantee that you'll be able to get a significant result. If it's less than 1, it will never be significant. If it's bigger than 3, it will be significant. So what about the 2.0s and the 2.1s and things like that, right? 2.0 all the way up to, say, 2.9. Sometimes you'll get an answer that's statistically significant, sometimes you won't. It depends on the alpha. See, if alpha is a nice big number, you'll get lots of these being significant. On the other hand, if alpha is a very small number, very few of these will end up getting you a significant result. Yeah. Let's see where we're going next. Okay, let's do the wolf one. Way back in the day when they didn't like wolves because they ate or attacked sheep and cattle and dogs and whatever. Probably not many people, but certainly livestock. The proportion of female wolves was about 50%, which kind of makes sense, right? Half the animals are male, half are females. You'd have a dominant male and a dominant female typically in a pack, but still 50-50. There was a large-scale reduction in wolves by hunting them, I'm assuming, and killing them in various ways. And instead of 50%, they believe that that has changed significantly, so that the population of wolves now has a lot fewer females than 50%. And in this story, 11 out of the 37 that they tracked were females. And they go in and they give you a reason why they think it's true, but nonetheless, it's still 11 out of 37. And the significance level that they're using is the hardest one to get over. It's the 1% level. So I'm going through this bit pretty quickly. 1%. Here's what we're trying to show, that it's less than 50. Okay, here is your null and alternate. One of them is the one you're going to use for less than 50. You got the right number, 4. Are we getting used to this sentence that's in every question? They just jumble the order. Why can you use the test? Well, you can use it provided. That's true. And never answer anything with a student T. We're doing standard normals and proportions. Now, these two are going to come from salt, and then the rest we'll do once we've got that answer. So I'm hitting salt. I'm going over here. One proportion, 11 out of 37. Is it less than 50%? That's it all set up. Right, 11 out of 37. Is it less than 50% was what we're trying to get evidence for. Generate results. Now, do you see that Z-score is a pretty healthy negative number, about negative 2.5, and the p-value is tiny, 0.0068. So there's my Z-score. There's my p-value. I'm looking for less than. So the picture that has a less than in it is that one. Do we reject it at that level? The answer is yes, because it's so tiny that you do that. It's less than 0.01 in this case, which makes it that guy, which makes it that guy. That is how quick that question could be done once you get up to speed. So far, so good? Okay. I'll skip that one. This one is loyalty to brand, I guess. Question 12. In the newspaper, US Today, I think it's a newspaper, 47% of general consumer population in the United States is loyal to the automobile manufacturer of their choice. So it's a bit like truck drivers, right? I'm a Ford guy, I always get Ford trucks, right? When my Ford truck dies on me, I go looking for another Ford truck, right? That kind of thing. Or I'm a, I'm a Chevy owner, or I'm a Honda, right? I always get Honda cars, whatever it is. And what they're saying here is that about 40% of the general population in the automobile industry are loyal. It's almost half, right? So when a person who owns a Ford vehicle goes looking for a new car, 50% of them go looking for another Ford, okay? Suppose that Chevrolet did a study of a random sample, oh, it's a huge sample, of 1,001 people. And they found out that 481 of that 1,001 said they'd buy another Chevrolet. Significance level 0.01. Does this indicate that the population of is more than 47? I guess that's saying, are Chevy owners even more loyal to their brand than the general population is? Now, more than 47 makes you that guy. And we are going to pick the standard normal where everybody's bigger than 5. Now I'm ready for salt. Oops, wrong guy. One sample. Number of successes, 481 out of 1,001. We are checking to see if it is bigger, more than 47. More than. Greater than. And the Z statistic is not that good. Do you see it's less than 1? Not good. And 2524 is the p-value. So go over here. That was the Z-score, 0.2524. We're looking at a greater than 47, and the answer is that picture, but it is not significant. The number is too big. It needs to be less than that number to work. So you do a picture with the left, it's not significant. and there's no sufficient evidence. So Chevy won't be able to claim that people like Chevys more than, you know, the other companies. And then I'll skip 13, it's pretty much the same. Okay, let's do a medical one. 14. Okay. This problem is based on information taken from the Merck manual. Now, this is a reference manual used in most medical and nursing schools. Has anybody here heard of the Merck manual? I haven't, but then I'm not a medical person. Okay, so evidently it's like the medical Bible, right? If you want to find out anything about blood pressure, you go and look at this manual. It's probably online now, like everything. And it'll tell you all the things that a doctor might want to know. I wonder if it's that thing where they put, you know how there's some rare diseases, like only 1 in 100,000 people have it? And so they put the information online, and probably the Merck manual online version. And a doctor's got a patient and he just can't figure out what the heck it is. The symptoms are just weird. And you could go and you could do a search, and it would come up with some candidates for possible diseases that would have that. And it might help them then say, wow, it looks like you're a 1 in a million person, right? There are only about 50 people a year end up with this disease, and you're one of them. Right. So let's see what they've got. Hypertension is defined as blood pressure reading over 140 and over 90 on the other one. So if you've got high blood pressure, right, hypertension, if it's not corrected, it can cause long-term health problems. So I'm guessing makes you more likely to strokes and heart attacks. In college-age populations, right, in young people, right, 9.2% have hypertension. That's about 1 in 10 people. We almost have enough people here in this class for one of you to have hypertension. That's not good. In that group then, right, 9.2%. Suppose that a blood donor program is taking place in a college dorm during the finals exam week. It's not a good time to do that. Before each student gives blood, they take your blood pressure. And so what they found was 28 out of 191 had hypertension, right? High blood pressure. And we are going to check at the 5% level whether that is significantly higher than 9.2. I haven't done this question. My gut feeling is yes. And the reason I'm going to pick that as a yes is, won't you be under a lot of stress during your finals exam week? And I believe stress is a big factor in high blood pressure, right? If you're under stress, you get high blood pressure. So let's get these guys out of the way, and then we can use salt. 5% level. Is it higher than 9.2? That makes it this one, right? Higher than 9.2. One of these guys, the one we pick, this time it's that one. Now I'm ready for salt. One sample proportion, 28 out of 191. And we want to see 0.092. We want to see if it's bigger than that number. Oh, nice big Z score. 14.6% of them. That's bigger than 9. P-value, pretty tiny, 0.045. So there's your Z score. P-value was, check it again, the P-value was 0.045. Now we're checking, is that less than 0.05? And the answer is yes. I don't know why this picture's a little bit funny, but it is what it is. And that makes it this one, which means that you do have statistically significant result. So you reject it and it's significant, so it makes it this one again, the same answer every time it's a yes. And this answer, it is. So what you could now say is that, yeah, 9.1 is bad, but it's even higher during the exams. Right? During the exams, it's almost 15%. That was quite interesting. And the next one's about blood pressure, so I'm not doing that one. Done the crime rate one. Oh. We have finished. Thank you. That's my dog. Tell me she wants attention. We've finished 8.3. Is there anything in 8.3 you want me to talk about? Because this is your chance. You feel comfortable with 8.3? Right. I know that you don't have enough time to do 8.4, and I certainly don't have enough time to go over all of it. But since we have the time, I want to use it. It's important. So I'm going to give you a little taster of what's going to happen to my other class on Friday. Right, the video that you'll maybe be able to skip the beginning of it because of this. So the last section in chapter 8 is testing for differences. Oh. Just waiting for it to load up. Okay. Here we go. Here we go. The one I'm going to do is the difference in population proportions. So I want you to imagine that you don't have one sample, but you have two samples. And one sample, you collected data from Americans. And the second one, you collected data on the French. And in the American sample, 41 out of 100 American adults said that they drank some red wine in the last week. So we will call this P1 hat. And they asked the same question to 250 French, and 120 of them said that they had drank some red wine in the last week. We're going to have a significance level of 0.05, and that's in the story. And we are now going to look at what the hypothesis test is. And it's going to be, is there evidence to show that French adults drink more wine than Americans? And it's going to be at the 5% significance level. So do you see what we've got here are two different samples, right? Population 1, Americans, population 2 is French. And we are going to take all this information and we are going to put it together and come up with a hypothesis test, which means that there's going to be a little bit of overlap between all the other hypothesis tests that you've seen, but it's not quite exactly the same as it. I'm drifting here right now because I'm trying to find the darn thing. You can never find it when you want one. Oh, here we go. So for this information, we are going to create a null hypothesis and we are going to use SALT to get a z-score and a p-value. And then we're going to do our test. And our test is going to be, is our p-value less than alpha? Now, although I'm only showing you one of these questions, and I'll show you one where we compare two means, once you've done one, you've done every single question, right? You just have to figure out how, where to get the numbers from. Well, the null hypothesis is P1 is equal to P2. In other words, these are the same. The null hypothesis is always going to be these are the same. So that's a little bit different. And in this story, to show that the French drink more than the wine, would you agree that that is basically how you would say P2 is bigger than P1? You actually phrase it as P1 is less than P2, but that's the same thing as this, right? Now, there are three versions of this guy. This would be French drinking more than the Americans. Wouldn't this be Americans drinking more than the French? And the third one is that they drink different amounts, right? They're not equal to each other. Left test, right tail test, two tail test. So it's not quite the same, but it's kind of like what we've done before. Agreed? Left, right, and middle. You're less than something, you're bigger than something, or you're not equal to it. The difference is that when it's a one proportion, won't this guy be a number? It'll be like 0.2 or 0.7 or something. So far, so good? Any questions before I move over and show you how you do that in SALT? Don't see any. So I'm taking it that we are good. And here is SALT. Now I'm clicking on this guy. Although you've never seen it before, can you tell by looking at this list that we're going to be looking at a two sample proportion? Does that name make sense because of the story? Two different proportions, two different populations. Now, the first one is going to be the Americans, and that's 41 out of 100. The second variable is going to be the French, and that's 120 out of 250. And now I have a problem here. So I'm going to have to go back and show you how to cope with the way that the software asks the question. They don't have a P1, P2, greater than or less than symbol, which is how I wrote these down. So let's show you how you convert them. The one that we're dealing with is that guy, and the alternate, right, was that guy. This is the same thing as saying the difference is 0. And this is the same thing as that the difference is less than 0. So if I go back now, I'll show you how we can do what they just said so that it works in Sol. The difference is 0, which is fine, and that it's less than 0. And now generate the results. You can see P1 hat, 41% Americans drink wine, 48% of French. That's pretty good. Not very good Z statistic, right? It's only negative 1 point something. And a bit too big, right? Isn't the p-value just too big to be significant? So it's 0.11 roughly. So I'd copy that guy. Right. Well, I don't have the data here, so I guess that's the best I would do. But we now have everything that we need. We'd write in Z statistic is negative 1.1, p-value 0.117, not statistically significant, failed to reject H0. So that would be the difference between what we've done with a single proportion and what we would do with a comparable one between two proportions. And for our last question then, got an awful lot of windows open here. Let's do a comparison of two sample means, or two population means. So we'll have population 1, which we'll have as females, and population 2, which we'll have as males. And we collected 100 people, 100 females, and we had a sample of 150 males. And the mean of this sample and the mean of this sample. So let's suppose we looked at the average age of college students, and we got 100 female college students, and we found out that their average age was 30.2. We did the 150 males, and we found that for the guys it was 29.8, that the standard deviation for the males was, female, sorry, was 1.9, and the standard deviation for these guys was 2.5. And that we want to do a significance level at 1%. So a story might go something like this. We're interested in finding out if the males and females at college are about the same age, same average age. So they got 100 randomly selected females, and they found that their average age was 30.2, and that the standard deviation of that sample was 1.9. And they did the same with the males, and they got this data. And now the question. Is there enough evidence to show that ages are different. It's pretty clear that the females are older than the males, but maybe we don't want to know that as a test. We just want to test, are they different? That's enough. Now, what will the null and alternate look like when you have two different populations? Well, you could have that, or I strongly suspect that salt will say that, which is mathematically the same thing. And the thing we're trying to prove is that they're different, which is that. And the way that will be written in salt is that the difference is not equal to 0. And so I should be ready to check this out. Oh, any gut feelings? Do you think that's a big enough difference to show up, or do you think they're too close to make any real significant conclusions? Do you think they're too close? Okay, let's find out.